Today we shall discuss about asymmetric slab waveguide. And its analysis and the properties. So, earlier we have discussed about the symmetric slab waveguide, where we considered the configuration as follows. The cross section N1 is the guide refractive index, N2 is the refractive index of the substrate, and cover also has got refractive index N2. In the case of asymmetric slab waveguide, we have a configuration where the cover refractive index is different, N3. So, this also forms a very important waveguide in integrated optics. So, we can say that the structure, the 3-dimensional structure of an asymmetric slab waveguide will look like this. We can say that if we take a substrate and make the whole top surface with a different refractive index, we get an asymmetric slab waveguide. And of course, cross section, as we have noted, is like this. For example, we can form this by diffusing. Just as an example, we can say that the formation can be found by diffusing impurities into a glass substrate as an example. And also we are considering only the step refractive index profile. So, the refractive index profile of an asymmetric slab looks like this. I would now put the coordinate systems, coordinate axis, and I will take the positive x axis down and this point as 0 and the depth as small d and so on. So, for x lying between 0 and d, the refractive index is N1, and is equal to N2 for x greater than d and is N3 for x less than 0. This can be said to be the refractive index profile, and we can graphically we can represent it as follows: n of x. So, in the covering region, when x is less than 0, it is very small, some value of N3, and in the guiding region you can say that it has got a value of N1, and in the substrate it has got a value of N2. Typically, if this is a glass waveguide, you know that the refractive index is around 1.5 of the glass, and if by doping with some impurities you can increase the refractive index by about 1% or so, slightly higher than the substrate, and if outside is air, it is equal to 1. That is the typical values. So, this is called the guiding layer, the substrate and the cover, the 3 layers, 3 different layers, and tentatively we will say that N2 need not be equal to N3, and usually for convenience we can also say that N2 is more than N3. So, it has got many interesting features like the cutoff of the modes, where the light is not guided beyond a certain wavelength, and the analysis of course is straightforward extension from that of symmetric slab waveguide, and we shall consider a scalar approach like what we did earlier for the symmetric slab waveguide, and solve for the modes of this structure and the expression for the propagation constant. We can start with the scalar wave equation. for the modes. That is like this. Where n is the refractive index profile, n is a function of x, and as defined earlier, the definition being definition of modes as they go as exponential e power minus I beta z, we will say that the modes are of the form beta z, where beta is the propagation constant and psi is the mode field profile. And for simplicity, I am using the same symbol for both, and by the context, you know whether we are talking about the z variation also along with the mode field or not. So, with this form for psi, this can be reduced to dx square plus k0 square n square minus beta square of psi equal to 0. So, we can split this differential equation into the 3 portions, psi 1, psi 2, psi 3 in each of these regions. So, in each of these regions we have the following form of the differential equations: d square psi 1 by dx square plus k0 square n 1 square minus beta square of psi 1 in the region 1, that is defined by x equals 0 to d, and d square psi 2 by dx square plus k0 square n 2 square minus beta square of psi 2 equal to 0 for x greater than d in the substrate, and d square psi 3 by dx square plus k0 square n 3 square minus beta square of psi 3 equal to 0 in the cover region for x. We can also call them as region 1, 2, 3. Region 1, region 2 and region 3. So, we can define variables to put it in a simplified form, and we know that the guided mode fields have the form of oscillatory nature in the guiding region, then exponentially decaying regions in the cladding and the cover regions. So, we can define this as a constant k. N1 recall is a constant, we are talking about the step refractive index waveguide, and we can call it as a kappa square or k square with k0 square n1 square minus beta square, and we can call this constant and remind that k is positive if beta is greater than k0 n1, and so we can replace this equation with d square psi 1 by dx square plus k square psi 1 equal to 0 as the differential equation region 1. And alpha 2 let us define as a positive quantity by beta square minus k0 square and 2 square, so that the equation becomes an exponentially decaying field minus alpha square psi 2 equal to 0, and in the region 3 also let us define by beta square minus k0 square and 3 square, so that the differential equation becomes d phi 3 by dx square minus this is alpha 2 and this is alpha 3 square into psi 3 equal to 0. Let us now choose the solutions based on the arguments that we have just now discussed, that the guided mode fields need to be oscillating in the guiding region and decaying in the substrate and cover regions. So, this will be possible if we choose beta to be lying between the values of k 0. So, this implies if beta should be less than k 0 and 1, and beta should be more than k 0 and 2, and beta should be more than k 0 and 3. So, since we said that n 2 is greater than n 3 just as a convention, because n 2 or n 3 which anything can be greater or lesser. So, if we say that beta lies between k 0 and 2 and k 0 and 3, we can say that we have a guided mode field. We can also represent it by using the number line for beta as follows: k 0 n 1 or n 3, k 0 n 3 and k 0 n 2 and k 0 n 1. So, this region corresponds to the guided mode fields for beta. Of course, as we have seen for the symmetric slab waveguide, it can take only discrete values and even single value, so that you have a single mode waveguide. Now, let us look at the solution of the fields in each of the regions. So, in the region where d square psi 1 by dx square plus k square psi 1 equal to 0, we have psi 1 equals a cos kx plus b sin kx, because we know this is the equation for a constant coefficients of the type of simple harmonic motion, and trigonometric functions are the solutions of this. Similarly, in the region 2, d square psi 2 by dx square minus alpha 2 square of psi 2 equal to 0. The solution is of the form psi 2 equals c into e power minus alpha 2 x. This is all oscillatory here and exponentially decaying here. So, we will not consider the field which is exponentially rising in this region. And we will ignore this function, and so we will not put e power minus plus alpha 2 x. So, we take only exponentially decaying field as a solution for this. This also implies that we are taking the boundary condition at infinity, that the field is going to 0 at x equals infinity. So, we have taken this as the origin and this is the d. Similarly, for the region 3, d square psi 3 by dx square minus alpha 3 square psi 2 equal to 0 gives psi 3 as d e power plus alpha 3 x. In this region also we want it to be 0, and since the x is negative in this side, we can choose the function which has got a positive value. So, as x goes negative, this decays to 0. So, we should note that we need both cos and sine terms as a solution of this differential equation. We cannot split these modes into symmetric modes and anti-symmetric modes as we did for the symmetric slab waveguide because of the asymmetry involved. So, we will also need the derivatives of the fields to be continuous at the boundaries. So, I will quickly find the derivatives of these also and write here. Psi dash can be given as minus K A sin K x. I will use some other color. Psi 1 dash to be minus K A sin K x plus K B cos K x is the derivative, and derivative of psi 2 is minus alpha 2 C e power minus alpha 2 x. Similarly, psi 3 derivative is alpha 3 d e power alpha 3 x. Our goal is to find the arbitrary constants a, b, c and d, and also the propagation constant beta, which is embedded in all these coefficients, in all these constants. So, let us apply the boundary conditions. We have seen that the boundary conditions reduce to continuity of the fields. And its derivatives across the boundaries. So, at x equal to 0 we have, I will always need this. So, this is 0, this is d, and this is psi 1 here, psi 2 here and psi 3 here. At x equal to 0, that is this point, psi 1 should be equal to psi 3. Which gives psi 1 and psi 3. When you put x equal to 0 here, A is equal to D. Similarly, the derivative of the field at this point, let me call it as equation number 1, and the derivative of the field also should be continuous at this point. So, we will call it as, substituting x equal to 0 here, Kb equals alpha 3, Kb equals alpha 3 into D. Let us call this as another equation. Similarly, at x equals D, that is at this point, the guiding layer and substrate interface, psi 1 equals psi 2 gives k cos kd plus b sin kd equals c e power minus alpha 2 x. This is one equation, and taking the, this has been obtained by taking the derivative, psi 1 dash equals psi 3 dash. Similarly, by taking psi 1 dash equals psi 2 dash, we get this and this. Okay, I will write here minus Ka sin Kd plus Kb cos Kd equals minus alpha 2 C e power minus alpha 2 D. We have 4 equations. We have many arbitrary constants a, b, c, d and also beta. So, let us eliminate some variables. So, from this we have, from the first equation we already got d equals a, and from the second equation we will get d equals, I will use the same board and same, d equals k into b by alpha 3, or the other way I will use it for finding out b. B equals alpha 3 by k into d, and since we have found from the first that d equals a, alpha 3 by k into a, these are the two constants we have eliminated, and by using the third equation we can get an expression for C. So, I can write C as e power alpha 2 d, and putting onto this side a cos k d plus b sin k d. Which we can replace for constants a and b using the earlier expression and write C as follows. C equals e power alpha 2 d cos k d plus b is alpha 3 by k into a. I will put a outside. We are not concerned with the actual value of a, so we will not try to evaluate right now. And in fact, when we are computing the mode fields etc., we can normalize it saying that the power is equal to 1 and evaluate a. So, we can use the fourth equation to evaluate the b rather than evaluate any other coefficient. So, by looking at these equations like what we did for the symmetric slab waveguide, we note that between these two equations we note that we can eliminate these exponential terms. This is d. We can eliminate these exponential terms by dividing one over the other. So, I will just divide equation 4 divided by equation 3. So, we can say, okay, let me use blue color, minus k a sin k d plus k b cos k d divided by a cos k d plus b sin k d, which will be equal to minus alpha 2 into c into e power minus alpha 2 d divided by c e power minus alpha 2 d. So, we can cancel out all the common factors and only alpha 2 remains here, and also we replace b with its value in terms of a. So, we get minus k sin k d plus b is how much, what is b? Alpha 3 by k into a, alpha 3 by k, already one k is there here, into a is cos k d, and this a I will take out common. Similarly, the denominator I will take out a common and say cos k d plus alpha 3 by k into sin k d, one more a out, equals minus alpha 2. This k can be cancelled out. So, I would like to simplify this expression by using the trigonometric properties of the trigonometric functions. So, let me cancel out this alpha also, so that there is a positive sign for this sign, and so I can, and also I will divide this throughout by k, so that you have alpha 3 by k, and also I will put it in form of tans. So, I will divide by cos also. So, I will try to get something like this, sine over cos minus alpha 3 by k, and sine is there here, one is there here, 1 plus alpha 3 by k into tan kd equals. So, I have divided numerator by k, I will also divide this side also by k, and this minus sign has gone with the other minus sign here. So, alpha 2 by k. So, let me represent this factor and this factor in terms of tan functions. Let me define phi 2 equals tan alpha 3 by k, alpha 2 by k, and phi 3, this factor, or the other way. Okay, let me put it in the form of tan inverse, so that, okay, I will redo. I will put alpha 2 by k as tan phi 2 and alpha 3 by k as tan phi 3. So, that we have tan kd minus tan phi 3 divided by 1 plus, which is 2, which is 3, tan phi 3 into tan kd equals tan phi 2. So, the left side can be written as tan kd minus phi 3, and the right side is tan phi 2. So, we can equate tan kd minus phi 2 phi 3 with phi 2 and add an arbitrary periodic constant m pi. So, the solution can be represented as kd minus phi 3 equals phi 2 plus m pi, noting that tan function is periodic with a period pi. In other words, we have got a solution like kd minus phi 2 minus phi 3 equals m pi, and replacing back phi 2 and phi 3 with tan inverse alpha 2 by k and alpha 3 by k, we get kd minus tan inverse alpha 3 by k minus tan inverse alpha 3 by k equals m pi. So, we can say that this expression represents the equation for arbitrary constant, propagation constant beta, which is there inside this k and alpha. This can be further simplified. We can put this in a very neat form. amenable for computation by manipulating some of these constants. Let me define a few constants that will simplify this. I will define a V number of the waveguide as Kd where I will replace the value of k as k0 square n square minus beta square n1 square according to the definition. Let us go back and see what is k. So, we have defined k as k0 square n1 square minus beta square. I will simplify this by defining an arbitrary constant, the normalized propagation constant. This can be called as V number. And I will to represent the beta, I will define a normalized propagation constant B. I will simplify that later on. B as beta square minus k0 square n square n2 square divided by k0 square n1 square minus n2 square. We will get to the logic of this definition in a minute. But before going further, let us simplify this further to write it in terms of B and the n1 square minus n2 square. So, I will add and subtract k0 square n2 square by combining beta square and k0 square n2 square. I can get d square root k0 square n1 square minus k0 square n2 square as one term minus k0 square n2 square minus beta square. So, I have taken this and this as the first term and this as a second term, which gives us, okay, let me divide with this term and multiply d into k0 square n1 square minus k0 square n2 square as one term minus k0 square n2 square minus beta square. I am trying to bring in this form so that I can write it in terms of B. I will divide by k0 square n1 square minus k0 square n2 square and also multiply with k0 square n1 square minus k0 square n2 square. So, we can note that this is equal to 1 and this is equal to small b. So, this is beta square minus k0 square n2 square. I think. So, this can be written as d square root of 1 minus small b and K0 I will put it somewhere here, and n1 square minus n2 square. So, I will define the V parameter to be as K0 into D into square root of this. Of course, there is a square root for this, n1 square minus n2 square. So that the factor k into d is V parameter multiplied by 1 minus b. I am starting with each of these terms. This K0d is V parameter 1 minus b. Let us look at tan inverse alpha 2 by K2 alpha 2 by K. So, alpha 2 by K can be written as follows in terms of V number and B. So, we have got the V number definition to be like this. So, alpha 2 by K can be expressed as beta square minus K0 square and 2 square according to the definition of this, divided by K definition is K0 square n1 square minus beta square. So, I will add and subtract. So, we need to get to beta square minus K0 square n2 square, and denominator K0 square n1 square minus n2 square. So, we have got n1 square only. So, we will add K0 n2 square and subtract K0 square n2 square. Of course, this is equal to alpha 2 square by K square, not alpha 2 by K. So, we will club minus K0 n1 square minus K0 n2 square and beta square minus K0 square n2 square. So, we can write this as equal to beta square minus K0 square n2 square divided by K0 square n1 square minus K0 square n2 square, one term, minus K0 square n1 square, K0 square beta is there here, minus beta into K0 square n2 square, beta square minus K0 square n2 square. So, by dividing by the numerator and denominator by K0 square n1 square minus K0 square n2 square, we can write this entire expression K2 square by K square as B divided by 1 minus B. Here also I will divide by K0 square n1 square minus K0 square n2 square. So, this entire expression is reducing it to beta by 1 minus B, B by 1 minus B. So, alpha 2 square by K square is written in terms of is equal to B by 1 minus B. So, only one constant B. You observe that the exercise that we are doing is to eliminate as many constants as possible to appear in this equation for the propagation constant beta. You have for alpha 2 by K, you have only one parameter B. Similarly, look at alpha 3 by K. We can now quickly write by the definition of alpha 3 beta square minus k 0 square n 3 square divided by k 0 square n 1 square minus beta square, not beta 1. So, once again like what we did earlier, we can manipulate this and get alpha 3 by k, once again alpha 3 square by k square in terms of small b. But here instead of n2 we have n3, our definition of b has got n2. So, let us convert this into n2 by adding and subtracting k 0 square n2 square by adding and subtracting square k 0 square n2 square. So, here we have k 0 n1 square, and so we can add and subtract like what we did for the previous case. We can add k 0 square n2 square, k 0 square n2 square. Alpha 3. So, because we need n2, we have added n2. Minus k 0 square n2 square, which gives us beta square minus k 0 square n2 square here, and k 0 square beta square minus n2 square minus n3 square. Beta square minus k 0 square has come here, this and this k 0 square n2 square minus k 0 square n3 square. Similarly, the below is k 0 square n1 square minus k 0 square n2 square and beta square minus k 0 square n2 square. This plus is combined with this and these are combined. Now, we can once again divide by k 0 square n1 square minus k 0 square n2 square and reduce. So, we observe that, okay, let me write afresh. So, this divided by beta square minus k 0 square n2 square divided by k 0 square n1 square minus k 0 square n2 square. I am dividing numerator as well as denominator by k 0 square n1 square minus k 0 square n2 square minus k 0 square n3 square divided by k 0 square n1 square minus k 0 square n1 square. Denominator also I will divide similarly, k 0 square n1 square minus, when we divide it becomes 1. Okay, let me write and then divide, k 0 square n1 square minus k 0 square n2 square divided by k 0 square n1 square minus k 0 square n2 square, and the other part beta square by k 0 square n2 square divided by k 0 square n1 square minus k 0 square n2 square. Now, this is small b and this is also the normalized propagation constant p small b. This of course is 1, and we will call this as some other arbitrary parameter a. So, this reduces to b plus a divided by 1 minus b. Let us define the parameter a as, I can cancel out k zeros appearing here and say n2 square minus n3 square divided by n1 square. I think this is n2 square, and this can be interpreted as a parameter depending only on the refractive indices n1, n2, n3, and since we have n2 minus n3 in the numerator, we can note that if n2 equals n3, this parameter a equals 0. That means, for symmetric slab waveguide the parameter a equal to 0. So, and also when n2 is not equal to n3, since usually the refractive index difference divided n1 square minus n2 square is very small, you can say that the value of a is very large. So, the value of a ranges from 0 for the symmetric waveguides and very large for very asymmetric waveguides. So, we can say that the a represents asymmetry parameter. A can be said to represent asymmetry parameter. So, with this we can rewrite our equation for modes of the asymmetric slab waveguide, characteristic modes of the asymmetric slab waveguide as v root 1 minus b minus tan inverse b by 1 minus b minus tan inverse b plus a by 1 minus b square roots equals m pi. So, we have reduced the equation in terms of very few variables. We have the variable, the V number, the normalized propagation constant, the asymmetry parameter and the mode index. So, mode index can be taken to be 0 for the fundamental mode, 1 for the next mode, 2 for next mode and so on. This equation cannot be solved directly in a closed form, but by using computer programs like MATLAB or Mathematica, you can easily evaluate all these variables or these constants. Given a V number, we can find the normalized propagation constant by using computer programs. Of course, these should be specific to only some symmetry parameter and some mode index. So, let me draw and we can interpret the modes of the waveguide, and before going further we can discuss about the nature of the modes. So, the V number on the x axis and B on the y axis, and of course, before you do that we can form a table of values of B versus B by programming or whatever way, and we can note that we get curves similar to what we obtained for symmetric slab waveguide, but there is a difference. We will note that soon. So, we can expect a curve that is like this, because B lies between 0 and 1 and gradually it reaches the maximum value, and the next one will start at this point and so on. So, we note that the cutoff values, that is when b equal to 0 are given by b equal to 0, and when we substitute b into this, we obtain the expression v equals v cutoff and b equals 0 in this, tan inverse 0 is 0 and here a remains, and minus tan inverse root a is m pi. this is the expression for cutoff. So, every curve starts at tan inverse root A. In the case of symmetric waveguide, A equal to 0 and there is no cutoff and the values will start at this point. I will draw with a different color to illustrate. So, the value this is, so these are all cutoffs tan inverse root A, and this is pi plus tan inverse root A, this is 2 pi plus tan inverse root A, and so on. That means every mode has got a cutoff, and for and this is mode index m equals 0, m equals 1, m equals 2, and so on. So, we are trying to observe the range of values of these curves, where do these fall. For a very symmetric waveguide, A is 0 and tan inverse root A 0, Vc is m pi. So, that means the first one will start at this, I will draw, I think. So, just a minute please, I think I will have to erase this and b equal to 0 and b equal to 1. So, this is starting at 0. Okay, I will draw again afresh. V number, normalized propagation constant b equal to 0, b equal to 1, and there is a cutoff tan inverse root A, and I am trying to observe the range of values of these curves. So, for symmetric waveguide they start here, and for highly asymmetric waveguide A is very large, tan inverse very large quantity is pi by 2. So, it can go up to pi by 2. So, this is 0, this is pi by 2. So, all the curves correspond, say this is the fundamental mode, all the curves corresponding to the fundamental mode for various values of asymmetries will fall in this, A equal to 0 here and A equals infinity at the other end. Similarly, the next modes will start at 0 plus pi and plus pi by 2. This is the range of values for the second modes, all of them will be following this. This is for values of asymmetry parameters from 0 to infinity, and this is for m equal to 0 and this is for m equal to 1, and so on and so forth. Using computer programs you can plot these and get an exercise of how they vary. Once again I would like to interpret what is the V parameter. We have got k0 d into square root of n1 square minus n2 square. So, the V number is a parameter representing, here you have the 2 pi by lambda representing the frequency or the thickness of the guiding region or the refractive index contrast of the waveguide. So, we can interpret wave V as representing normalized frequency or normalized thickness or the normalized refractive index contrast. B also, once again we said that it is normalized with respect to beta, it is representing beta. Finally, we can look at the modes, nature of the modes. N2, N1, N2 and N3. We observe that the contrast is small, and so we can expect the alpha 3 to be very large here, and gradually decaying this side. We can expect that it is not coinciding in the middle, but somewhere offset towards the air region, and alpha 2 is small, so we can expect a longer trail. So, there is an asymmetry of the exponential trail as well as the oscillatory field. By similar arguments we can note the properties of the next modes. So, we have taken a scalar approach, we can relate what all we have done with vector modes like TE modes, TM modes, etc., or modify this approach slightly to represent the vector modes more accurately. Thank you very much.